Hello and welcome back. We're on lesson number 3 today. We're talking about something called standard deviation. Now this is a very statistics type of thing that we're looking at. It is a little bit of a process, so be prepared for that. I'm going to try to keep this short. I only made this like a couple of pages long, so hopefully we won't go too far into time with this. Standard deviation. So here's what it is technically. It says it's a quantity that measures the dispersion, how far apart of a set of values are. We use sigma, which is this little like kind of sideways 6 little symbol. It's the lowercase of the sigma that we were using that kind of looks like that capital E3 combo thing. Okay, but anyways, this is not the clearest definition in my opinion, because it's very mathy. If you break it down into common terms, there's a distance between every single number that we have in a set, right? If you think about all the quiz grades, some of you guys get quiz grades that are like, I don't know, as far low as like a 55, and some of you get as high up as 105, right? So you have that range right there. But in between, you have all these people getting different scores. Now, the distance between some scores, you could have some people that all score an 80, in which case there'd be no distance between them. And then you could also have some people who are scoring an 83, in which case there'd be 3 score units between, right? Then maybe the next score after that is an 85, right? So there's all these distances between the scores. And if we want to find the average distance between, that's what a standard deviation is. And what that helps us figure out is much more clearly where data is lying. It's going to put it into a nice distribution curve for us, and we can see much more clearly where overall populations will fall, especially when we're looking at a smaller sample size. So that's the definition of standard deviation. Variance, it's just something that we need before. It's the average of the squared differences from the mean. That is the variance. On its own, I'm sure that there are things that we can do with it, but we're not going to be doing much with it other than finding the standard deviation, which is the square root of the variance. So the variance is really the stuff that takes us the most amount of time. Standard deviation is just a quick square root of the variance. So here's what you're going to do. These are the steps to finding standard deviation. First, you're going to find the mean. That's the same mean sum average that we did in lesson 1, right? You add everything up, divide by the number of elements. There's a symbol now for this, which we're going to use x with a little straight line over it. It's not the same thing as x without a line over it, right? Those could be 2 different numbers. This is specifically the mean average. Second thing, you're going to, for each value, subtract that mean average and then square. I'll explain that part in a second. And then finally, find the mean average of this new set. Because you did this for each number, you're going to have all these new numbers that you're going to now have to find the mean average of. So what this just did, subtracting is finding you the distance. But because distance is always positive, we need to square that number so we get a positive number. But we just changed everything so substantially by squaring it that we're now going to have to take the square root to get back to that average that we really wanted beforehand. Okay, and that's the variance. So when we take the square root part, would give us our standard deviation. Okay, so we're going to do that. Pretty easy to do. It's just a lot of work. So I made sure that I didn't give crazy large sets of numbers. And they don't have to be in order, which is another good thing. We can just do this straight through. So the first thing we've got to do, calculate the standard deviation out of the nearest hundredth, so 2 decimal places. First thing we need to do is find the average, the mean average. So let's just go ahead and add these up here. We got 810 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our average here is 81. That was step 1, find the average. Step 2 said for each of these numbers, you have to subtract and then square. And the squaring part comes in really clear right here because 74 minus 81 is -7. But we don't want negative distances, so we're going to square that, and it's going to give us 49. And I'm going to write that new number down here. And I know eventually I'm going to have to add these and find the average. So I'm going to keep on doing this for each of these numbers here. Oops. What's really nice too is I have 82 showing up a couple of times, so I can really quickly write that down twice. I don't have 74 or 64 showing up again, so I don't want to do that for those. Let's see, I'm kind of running out of space. I'm going to do a little bit down here. A couple more to go. And finally, we have okay. So step 2 was to find all of these numbers, which I did, and I listed them, but I'm taking a little bit of a shortcut. I'm going to put these pluses in between right now. I also took a shortcut because I noticed that this showed up twice, so I kind of cheated and did that twice real quick. But no big deal. We have all the numbers we need. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there were 10 to start. We should be getting a new set of 10. So we're going to end up adding all these together and then dividing these by 10. So let's take a second to add these up. 49 to 89. $1,190 divided by 10 is 119. That's the variance, though, right? We just took all this time, 1, 2, 3, to find the variance. Right, so your variance equaled 119. That's not what they asked for, though. They asked for standard deviation, which is sigma. Sigma is equal to the square root of that number. Second root 119. So the nearest hundredth is 10.91. That was not the clearest organization. You can see exactly what we did. I wasn't very talkative during it because I just wanted to get it done. But that followed all the steps exactly how we did it. So if you need to look at your steps as you do this one down here, go for it. But pause the video and resume when you're ready to check this one. All right. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So we're going to add all these up and divide by 10 to find the mean average first. So we found our average to be 82. So now what we need to do is take each of these numbers, subtract that, and then square it. Does that show up twice? Yes, it does. So I'm going to go down here as far as I can. 92, 92. 80. Maybe show up anywhere else? Nope. 68. No other 68s. 95. Again, if you need to skip over this because it's just kind of me doing all this stuff out, not very talkative either. If this is helping you to make sure that you got everything, that's cool, but you don't have to watch all this. Let's see. Oh, I did that one wrong. It's 82. See? 67 minus 82 is 15. Two more to go. And then 82 minus 82 is 0, which we don't even really need to do. All right, so we add all these up. There's 10 total divided by 10. 100 plus 100 plus 4. 6 plus 169 plus 0. Why not? Ooh, 1,000 is 100. So we found our variance to be 100. If we want standard deviation, we take the square root of 100, and we get a standard deviation of 10. What that means is that when you look at all these original data scores, yes, some of them have a pretty close distance to each other. Right? I don't have any of these in order, but if you were to look at like 82 and 80, right, those are only 2 apart. But there's also a gapping so large between some of these numbers. I believe the average distance would be 10 between them. So that's what standard deviation is. That's how you calculate it. There's a little bit more left to go with this lesson, but we're actually almost done. We're going to look at the normal distribution curve again, the bell curve, if you remember from last time, but we're going to look at some more specifics about it. Okay, if you want to take a second to pause the video and copy this down, I'm going to go over this with you right now. So when you look at a normal distribution curve, this bell curve, when you find the standard deviation, everything should fall generally into this pattern. What's really cool is if you look at probability in the Boston Museum of Science, they actually have this huge thing that drops all these little balls and they randomly fall down, and randomness usually falls into this almost every time. I mean, it's so improbable that it wouldn't. It'll show up in this general format almost consistently for all eternity. Anyways, the way that this would work, you have your average in the very middle right here. That is your average. And then as you start to space yourself out according to your standard deviation, if you're adding a standard deviation going towards the right or subtracting it going towards the left, you can start to see the spread of the data. And what that means is that if you were to look at, I don't know, the last sample that we had only had 10 people, which isn't the greatest sample source. But if you were to look at like hundreds or even thousands of people in a population or sample, and you start to see the average and standard deviation, you can now start to see where percentages of the population happen to fall. And I have this broken into two different categories. I have it broken up into these sections, which tell us between here and here, right, the first two standard deviations, first standard deviation to either side. 68% of the population falls in this category. So you're either at the average or you're a little bit above or below average in that standard deviation. That's where 68% of us fall. 95% of us fall in between these two standard deviations from the mean, and then 99.7% live live within 3 standard deviations on either side. That should make sense that the bulk of the population isn't here. What should also make sense is that anything outside of those is much, much less, significantly less. And that's where we can start to talk about significance, right? When you look at bits of data or even probability for that matter, when you have something that falls less than 0.3%, which is 0.003, so anything less than 0.003, it becomes in some cases less significant, or in other situations they call it what's the word I'm looking for? Let me look it up here. Unusual. Okay, so it's not usual for things to fall outside of here. It's much more usual to fall within these boundaries. Now, there's also some other ways that I wrote this out too. I did this out for you, but basically if you start from here and go this way, you can now start to see how much percentage of the population falls covered, right? So from here, right, anybody who scores less than this would be, or up to 3 standard deviations under, only 0.15% of the population fall into that category. So that's what I'm trying to show you. 0.15%, not even a whole percentage. Right, so it's very few that fall into this category. It would match on the other side, but as we go across, right, up to this 2 standard deviations away, 2.5% fall in that category. Then you got 16%, and then 50% is going to fall within the first, or within the average, right? Half of us have to be less, half have to be greater. 84% fall within 1 standard deviation. Right, so now you can start to see where they have the idea of somebody like a valedictorian being so important, because if this is the average test score, only so many people are going to score up here. And when you talk about a college or university, you have hundreds of people graduating. You're only going to have a very rare, unusual amount of people who are scoring perfect scores. Right, so now you can start to see where this data display really kind of helps to show where things are, right? Almost everybody, 99.85%, fall less than 3 standard deviations above the standard. If somebody was to score even a little bit more, that's considered unusual. So let's get to the couple of questions we need to do. right? That's the information that we need. I'll go back to that in a second, but you will be able to refer to it because hopefully you wrote it down. They tell us that the average weight of a watermelon in this example is 20 pounds and the standard deviation is 0.9 pounds. By the way, I looked that up on Google. That is what they told me as far as the average weight. So they want us to make a normal distribution curve and then answer these following questions underneath. So first of all, the average weight, this would be X with a line above it. The mean average is going to be 20. On our line plot, the very middle of this is going to say 20. And they give us a standard deviation, sigma, which is 0.9. So as we start to fill out the rest of this, we need to be adding 0.9 as we go along this way to the right and subtracting it this way to the left. So if I start going to the left, subtracting 0.9, we get 19.1, 18.2, and 17.3. If I start at 20 and add 0.9, we get 20.9, 21.8, 22.7. Okay, so these are weights in pounds of watermelons. If the average is 20, and then the standard deviation between them, that's how much weight, a little bit less than a pound difference. So they should all be pretty close to the same weights as they come out. This bell curve, just do your best trying to draw it. I believe I put little dots to start to kind of like show me where stuff is going. Okay, but now we have these that match up with this information up here, and it's very useful because when they start asking us some questions down here, what percentage of watermelons weigh below 21.8 pounds? Here's 21.8. It's 2 standard deviations out, so 90. What is that? 97.5% weigh below 21.8 pounds. So if you were to look at all the watermelons in this sample, almost everyone that you pick up is going to be less than 21.8 pounds. What percentage weighed less than 17.3? Well, anything that was less than that weight for this particular sample was not very usual. Could there be one or two? There had to have been in order for us to have that average, but it's not very usual. Not likely that you pull out a 17.3. What percentage falls in that category? 0.15. Now, working with these percentages, if we know amounts, right? They tell us that there are 300 watermelon that were used in this survey, how many weighed less than 20.9? So we can actually get the number of watermelons. So 20.9 is right here. It matches with 84%. So if I take 300 and multiply by 0.84, that'll be the number of watermelons that weighed less than 252. So 252 out of 300 fell into this weight range. All right, I've got one of these for you to try out, and I believe that's the last problem for this video. So pause the video and resume it when you're ready to check. Oh, I'm sorry. You couldn't do that because you need the problems. So here are the problems. All right. Let's see. I can zoom out and I can see all this at once. All right. So people eat an average of 11 pounds of chocolate per year. Again, I looked that up on Google. So our average is 11. I made up the standard deviation, though. I want it to be reasonable. 1.1 pounds. Because some people don't like chocolate or don't have as much freedom to eat it as others. So if we start adding 1.1 to both sides, that would be 12.1, 13.2, 14.3. If we do subtract on the other side, 7.7. Okay, and then again the curve, just do your best to draw it out. I put little dots beforehand to kind of help. Doesn't really matter. All right, so let's see. What percentage of people ate less than 9.9? So here's 9.9. Real quick, just flipping back here. Looks like that's where the 16% was. What percent eats more than this? 14.3. So here's 14.3. It was at the 99.85. But if they're eating more than that, then out of the 100%, we'd want to get rid of this. So 100 minus 99.85. So 0.15. That was a little tricky because you had to think about backwards getting rid of. If you ended up at this number, you were close. But remember, very few people fall into that category. And then finally, out of 520 people that were in the sample, how many eat less than 8.8 pounds in a year? So here's 8.8. That would match with the, let's go back here, 2.5. So if we change that to 520 times 0.025, looks like only 13 people ate less than 8.8 pounds of chocolate in a year. So hopefully you did okay with those. That's how you use standard deviation and how you can read it off of a normal distribution chart. And you can see now, hopefully, that these are pretty useful, especially when you start applying them to more important research, medical research, and that type of stuff. I guarantee you uses very easy to read charts like this, especially when they're looking at like maybe a new pharmaceutical product. But anyways, that's it for this video. We're all done. We got one more lesson to go for the live videos for this unit, and I believe that should be it for Algebra 2. Just one more video. So I'll see you there. Bye.